All right, I'm gonna do some of the homework problems. Whichever ones I don't get to will be posted. I'm gonna do a couple in chapter 19 and then do a bunch in 20. Let's see. I'm gonna do 19.90. That's using the Nernst equation, which is your E is equal to E naught, so your E cell is equal to your E naught cell minus RT over NF ln Q. All right, so you might see a little bit different version on the homework, on the book, whatever. This is the one I always use. All right, so this E naught cell, this is what you get off of table 19.1. This is what you read off your voltmeter, or it's what you're calculating. R is always 8.314. T is always 298 in this chapter. And F is always 9.65 times 10 to the fourth. The N you have to get from the reaction that is going on. It's the number of electrons gained, which is equal to the number of electrons lost. So your N is your number of electrons. Your Q is the same setup as K. So when you do your Q, it is your concentration of your products. If they are aqueous, it has to be in molarity. Or if it's in a gas, you have to put pressure of your products. All right, and that has to be in atmospheres if you're using pressure. So all concentrations are in molarity, and it's always products over reactants. So any gases have to be put in atmospheres. Any ions have to be put in molarity. It's the products over reactants, same setup that you have for a K, except Q is not at equilibrium. All right, so in 1990, it says the cell potential for the following cell at 25 degrees Celsius is 0.480. All right, so they're giving you the E cell, 0.480 volts. And then they give you the cell notation. Zinc plus 2, and that is 1 molar. Then you have H plus, and that is the question mark. They say that is going to be the question. What is the concentration of H plus? The actual question is, what is the pH? In order to get the pH, you have to have the concentration of H plus. H2, and then since they're, okay, this is 1 ATM. All right, and then platinum. All right, the zinc and the hydrogen could be any molarities, any pressures. All right, it doesn't matter. They do not have to be one. They're whatever is given. All right, so then the question is, of course, calculate pH. All right, so we have to write our cell reaction. And so this is always anode. Then you got your salt bridge and cathode. That is how you always write a cell notation. And so the anode is oxidation. Zinc goes to zinc plus 2 electrons. If you look at table 19.1, it gives you the reverse reaction because that's all reduction potentials, not oxidation potentials. And so you take the opposite sign of that number. And so when you look that up, it is a 0.76 volts. So your E value here is 0.76 volts. All right, so then your other one is the standard hydrogen electrode, where you have 2 H plus and 2 electrons going to H2 gas, and your E value for that is 0 volts. Your standard hydrogen electrode is 0. So on table 19.1, the reduction of zinc is negative 0.76. So the oxidation of zinc, the reverse reaction, is positive 0.76 volts. All right, and so then you add that up, of course, you have 0.76 plus 0, so your E cell, your E naught cell from table 19.1, 0.76 volts. And that's what's going to go here, 0.76 volts. All right, and also from writing these cell reactions, you see that your N value is 2 electrons gained, 2 electrons lost. So now we have our value for N. It is 2 moles of electrons. Now we write the overall reaction. The overall reaction is zinc plus 2H plus yields zinc plus 2 plus H2 gas. And so your Q is the same setup as your K. It is products, zinc plus 2 concentration, pressure, hydrogen gas, divided by H plus concentration raised to its coefficient of 2, H plus squared. Zinc solids, solids, and liquids are not put into your K and therefore not put into your Q. All right, so it didn't have to be 1 molar for zinc plus 2, but whatever concentration is given for zinc plus 2, you plug that in there. It was given as 1 molar. Your pressure of hydrogen didn't have to be given in atmospheres. It didn't have to be given as 1 atmosphere. It could have been millimeters of mercury, which you convert to atmospheres by dividing by 760. But in this example, it was 1 atmosphere. And H plus squared, that's what we're looking for. Once we find the concentration of H plus, then we take the negative log of that and we get the pH. All right, and so now we just plug it all together. So your 0.480 is equal to 0.76, that's volts, minus 8.314 joules per mole Kelvin, 298 Kelvin, over moles of electrons, 2 moles of electrons, and F 9.65 times 10 to the 4th coulombs per mole of electron. And now the ln of Q, which is equal to, 1 times 1 is 1 over H plus squared. So that is your Q. So again, you have one unknown. That one unknown is H plus. You solve for H plus. All right, and so to solve this, we subtract 0.76 from both sides. And we get a negative 4.7618. So we get, what the heck is that? All right, so we got 76 minus that, 862. 0.28 negative 0.28. Shouldn't have been that hard. All right, negative 0.28 volts. Negative 0.28 volts is equal to, and then we're going to multiply all those things together. That is then negative. All right, so you got your 8.314 times your 298 divided by 2 and divided by 9.65 times 10 to the 4th. All right, and so minus a 0.02012 ln 1 over H plus squared. All right, to get rid of that, we divide both sides by negative 0.0128. Negative 0.128. And you get 19.5. So you get 19.5 is equal to the ln of 1 over H plus squared. Now you push your e to the x button. And you get a very large number. So you get a 2.87 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 is equal to 1 over h plus squared. Invert both sides. So inverting that, x to the minus 1, you get a 3.485 times 10 to the negative 9 is equal to h plus squared. Take the square root of both sides. And you get 5.9 times 10 to the minus 5. All right, but the question was, what is the pH? And the pH is equal to the negative log of your H plus concentration. And your pH, when you take the negative log of that, you get 4.23. All right, that is not what I got the last time I did it, so I did something wrong. Not sure what that is. All right, I took your 0.48 minus the 0.76, and that is negative 0.28. All right, all my numbers are the same, but I got a pH of 4.73. What'd you get? 4.74, okay. So I pushed the button wrong somewhere. 4.73 is what I got, but of course, if your number is different in that decimal, that is fine. I'm not seeing what I pushed wrong right now, but I pushed something wrong. Let's try that again. 8.314 times 298 divided by 2 divided by 9.65 4 28. All right, 0.28 divided by that. No. All right, so that was 21.8. I don't know what the hell I pushed. But anyway, it's 21.8 here, not 19.5. And then you push your e to the x button. And that gives you a 2.97 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Invert that. And 3.37 times 10 to the minus 10. All right, then the square root of that. And you get a 1.8 times 10 to the minus 5. And then the negative log of that. And you get your 4.74. Right. Keep all of your sig figs, it would be a 4.74 as your pH. Not sure what number I pushed wrong, but anyway, that is the answer to that one. All right, let's do electrolysis problem. Let's do 1998. All right, so this is electrolysis. So the equations, Q is equal to NF, Q is equal to IT. There will definitely be problems using these equations. And so if Q is NF and Q is IT, then NF is equal to IT. All right, the key here is time has to be in seconds. not any unit of time, must be in seconds. Current is always in amps. There is not any other choice. You're going to have always current in amps. N is not moles, it is moles of electrons. That is a very important designation. It is just not moles, it is moles of electrons. All right, so it says how many grams of cadmium are deposited from an aqueous solution of cadmium sulfate. So you got your cadmium plus 2 electrons going to cadmium solid. All right, and so you're going to have a current. Anytime you are given a current, you know that you're using this equation. This is the only time you're going to have amps. All right, so you have your I value. It's given 1.75. And it gives you a time, 325 minutes. You must immediately convert that to seconds. If you put in minutes, you get the wrong answer. It must be in seconds, because an amp times a second is a coulomb. An amp times a minute is not a coulomb. It has to be in seconds. All right, and so there are 60 seconds in a minute. So you immediately multiply that by 60. All right, and so of course F is a constant, so we can solve for N. N is equal to IT over F. And so your current is 1.75 amps. Your time in seconds is 325 times 60 seconds divided by 9.65 times 10 to the fourth coulombs per mole of electrons. And an amp times a second is a coulomb. So an amp times a second cancels the unit coulomb. All right, and so you got your moles of electrons. You push the buttons, 0.35 moles. All right, but the question wasn't moles of electrons. It was mass of cadmium. So you look at your balanced reaction, your half reaction, and you see that you have 2 moles of electron for every 1 mole of cadmium solid. All right, but it didn't ask for moles of cadmium solid, it wanted mass. So then you go to molar mass, 112.4 from the periodic table, grams per mole of cadmium. And you push the buttons and you get 19.9 grams of cadmium will be deposited if your current is 1.75 amps and your time is 325 minutes. All right, let's do some chapter 20. Let's do 2042. Reach the following, choose nuclide that is radioactive or unstable. It's going to do radioactive decay. And the other one would then be predicted to be stable. So if we look at silver 102.47 versus silver 109.47. All right, so we want to put our protons and neutrons down. So here you've got 47 protons, and when you subtract them, you have 55 neutrons. Here you have 47 protons. If you are silver, you're 47 protons. And when you subtract that, you got a 62 neutrons. All right, so here I see 2 odd numbers. These are both odd. The chances of that being stable are very, very, very low. So you would predict this one to be radioactive. So this one would be radioactive. And so one is radioactive, then you predict the other one to be stable. All right. erased a bunch of stuff. All right, so that was 55 neutrons. This is 47 and 62. So this is odd and this is even. All right, and so there is a much, much higher chance of that being stable than two odd numbers. Mg 2512 versus Ne 2410. All right, so here we have our protons 12, neutrons 13. Here we have protons 10, neutrons 14. All right, so if we look at the periodic table and we look at our molar mass of neon, we see that your magnesium molar mass is right at 24. So here it is, magnesium 24.305. All right, so molar mass 24.305. And when you go to neon, and it is 20.18. All right, so when you have a mass that is far off from its molar mass given on the periodic table, the chances of that being stable are a low chance. And so with your magnesium, molar mass being 24.3 on the periodic table, the chances of a magnesium 25 being stable are pretty good. And so you would predict this one to be stable. It is very close to the molar mass on the periodic table. And you would say this would be unstable. And you know that this is a high mass isotope. All right, and so you know your two choices are going to be a beta or a positron emission. All right, so if you do a beta emission and you have your 0 and your -1 for your beta, this would be a plus, a 24, and an 11. And so that is the correct mode of decay, because now we have a higher atomic number. All right, and so we didn't add any mass to it, but we have a higher atomic number to count for this higher mass. And so when you look at sodium, it is right at 23. And so a sodium 24 would be expected to be definitely more stable than a neon 24. All right, and so you have a very high mass because it said 20 and not 24 on the periodic table. And so its decay mode would be a beta emission. The last one is very simple because of what you need to know. So you got your TL20381, and you've got your TH22390. All right, as soon as you see that this is less than 81, but you see this is greater than 83. So when your atomic number is greater than 83, you are radioactive. All of them are radioactive. So this is known to be radioactive. And so you would predict, if you're going to predict one is radioactive, you know that one's radioactive. So yes, you predict that to be radioactive. And if the other choice is stable, well, then this one must be stable. All right, and so if you are greater than 83, your predicted decay mode is alpha emission. So your 22390TH predicted mode is going to be a alpha emission, which is 4,2, which means you have a 119 left here, and you're going to have 88 there. And when you look on the periodic table and find atomic number 88, you see that that is Ra. Right, so you need to know if you have a high mass isotope, you're going to do a beta emission. If it were a low mass isotope, you would do either a positron emission or an electron capture. Either one would give you the same product nuclei, which is 20.44. So we kind of combined those two problems. All right, so that first one says you have a zinc 60-30. So you look at zinc on the periodic table, find its molar mass to be 65.38. So molar mass, 65.38 grams per mole for zinc. So you see that this is a low mass. Right? You just compare it to the periodic table molar mass. It's supposed to be a 65. This is a 60. That is a low mass isotope. All right, and so you can do an electron capture. All right, so you have an electron. You have to know 0 and -1 for the electron. So you got 60, and you have 30 minus 1, which is 29, and the periodic table, copper, is 29. All right, so it's getting closer. So it went from a 65 down to a 63. All right, it's still a low mass isotope, so copper 60 would also do an electron capture. But note, if you say it undergoes electron capture, that is full credit. If you say that it decays, so you're going to emit something, that would be a much better answer. All right, it's going to do a positron emission. A much better answer is the actual decay mode is a positron emission, but usually the question is, what is your product? And so the product would be the same regardless, a 60-29 copper. So the actual emission, the radioactive decay mode, is a positron emission, but you would get that same product from a electron capture. All right, the next one is a carbon-10. We all know carbon is supposed to be 12, and so your carbon-10 also is going to do a positron emission. That is a 5 plus 1 is 6. All right, so 5 is boron. So if you look, carbon should be 12, not 10. So it's a low mass. Boron should be a 10.8 instead of a 10, but that's much closer than the 12 is to 10. And so you're getting down to a correct mass isotope, very close to the atomic mass number. And then, of course, we already did this one. If you have a atomic number greater than 83, you're going to predict a alpha emission. So you have to know that alpha is a 42. That is 241, I believe. All right, and so that is a 237 on top, plus 4 is 241, and a 91 on bottom, plus 2 is 93, and 91 on the periodic table is PA. All right, so you need to know your different decay modes. So we already did, if you have a high mass, that was in the other example, you're going to do a beta emission, low mass positron emission. A atomic number greater than 83, you're going to do an alpha emission. Those are your 3 predicted decay modes that you need to know. All right, then you have the really easy questions like on 20.48. All right, I'll do part B. That is copper 63. Is getting an alpha particle. All right, so we're bombarding it with an alpha particle, and it is ejecting a neutron. And then I usually don't give the other product. There's always some question here. All right, so then it's going to be, what is this product? And not, here's the product. All right, so we see we have a 67 on top, 63 plus 4. And so we have a 1 plus 66, all right, will give us 67 on top here. On bottom, we have a 29 and a 2, that's a 31. We have a 0, so that has to be a 31. You go to the periodic table, you find atomic number 31, that is Ga. All right, so there is your balanced reaction. Now we put it in a notation. And so our target nuclei is the copper 63. All right, it is bombarded with alpha particles. You need to know the symbol and the symbol for alpha and know that that is a helium-4 it ejects a neutron, and the product molecule is a Ga6631. All right, so you have to be able to write the reaction and put it in a cell notation or a notation form. This is not chapter 19. All right, so this is a nuclear bombardment reaction. Let's do 50. B, also a very simple question. It is the same, but it gives you the notation and you have to write the reaction. So on the test, it's going to be Cu 6329, and it's going to have P, it's going to have comma, it's going to have N, and it's going to have question mark. All right, it's going to say write the balanced reaction and give the unknown product molecule. All right, so you got your copper 6329. You've got your proton. You have to know that a proton is either P11 or H11. I would accept either for proton. Neutron, you have to know that that is one neutron, 0 protons. So you have to know the numbers that go with that. All right, so then on top, you got a 63 and 1 is 64. So same thing here. You're going to have a 63 and 1, which is 64. On bottom, you got 29 and 1. That's 30. You have 0 and 30. You go to the periodic table. Look at element number 30. That is zinc. And so to finish that, you know that that is a zinc 63 and 30. All right, so those will be the easiest problems on the test. Do not miss the easiest problems on the test. 54, also very, very simple. All right, fill in the missing particle. You've got your 2054. So in part A, you've got aluminum 2713 plus tritium H31 going to magnesium 27 and 12. All right, so on top, we got 27 plus 3, that's 30. On top, we're going to have 27 plus 3, that's 30. On bottom, we have 13 and 1, that is 14. Here we have 12, so we need 2. And 2, atomic number, go to the periodic table, that is helium. That is not an alpha particle. An alpha particle is a helium-4 All right, in part B, all right, here is a notated form. We got carbon 12 plus a tritium H31. That's going to give off a particle plus a carbon 14. All right, so on top, we have a 12 and a 3, that's 15. We have 14 plus 1, that's 15. On the bottom, we have a 6 and a 1, that's 7. On bottom, we're going to have a 6 and a 1. All right, and so that is a proton. So we have our cell notation, or our notation for this bombardment reaction is a carbon 12-6. You have a tritium, you have a proton, and you have a carbon 14-6 for the notation for that reaction. All right, 56. On 56, we got californium bombarding element with alpha particles. The products were californium and a neutron. All right, so the products were californium. All right, so you don't have to know what that is as long as you see the 245. You go to the periodic table, look for a molar mass of 245, and you see a 251, that is CF, and the chances of that being californium are 100%. So we have a 245, and then californium is number 98. All right, and we also, products were californium and a neutron, plus a neutron, 1, 0 for neutron. All right, and a target was bombarded with alpha particles, which is a helium-42. And so the question is, what was bombarded with a helium-42 nucleus to do this? Well, again, it's just the numbers. You got 246 here, so you got to have 246 here. 242 plus 4 is 246. So we know the number on top is 242. On bottom, we know we got 98 on this side. This is a 2, and a 2 plus a 96 is a 98. So we got a 98 equals a 98. And then we go to the periodic table, look at 96, and that is Cm. All right. So that is your target element. So that's your target. Here is your incoming particle. All right, so the notation, Cm, 242, 96. You've got alpha, you've got neutron, you've got CF, 245, 98. That is the notation for this nuclear bombardment reaction. All right, 2058. The first isotope plutonium-238. It is used for batteries. Okay. All right, so we got a sample of plutonium-238 weighing 2.8 times 10 to the minus 6 grams, or 2.8 micrograms. The decay rate, all right, so decay rate, that is your K. All of your radioactive decays are first order. All right, 1.8 times 10 to the 6. Disintegrations per second. All right, so that is the rate, not K. That is not the rate constant. That is your rate. All right, so that is the rate. What is the decay constant? So the question is, calculate K. All right, and they want that in units of 1 over seconds. So rate, first order rate law, rate is equal to K N T. This is nuclei at that time. All right, and so what we have is the rate. The rate is given. The rate is given in the correct time units. We want that in seconds. It's in seconds. Disintegrations per second. All right, but we have to get our NT. The units for this is nuclei. All right, so we have to have nuclei here. We have to use Avogadro's number to get that to nuclei. So we have 2.8 times 10 to the minus 6 grams of plutonium-238. So, of course, the molar mass of that is 238 grams per mole. All right, so that's moles of plutonium. We want nuclei of plutonium. So there are 6.022 times 10 to the 23rd nuclei per mole. And so the moles cancel, the grams cancel, and you get the number of nuclei. And so you have your rate, 1.8 times 10 to the 6 disintegrations per second. That is equal to K, what we're solving for, times when you multiply that, you get 7.08 times 10 to the 15th nuclei And so this is nuclei disintegrations per second. Here's the number of nuclei. The nuclei cancel. And you have your K value in 1 over second. So you divide both sides by 7.08 times 10 to the 15. And you get your K in 1 over seconds. That is 2.5 times 10 to the minus 10. All right, so let's get the half-life. Although I think that's the next question, but what's the half-life? So your half-life is 0.693 over K. And so it is 0.693 divided by the 2.5 times 10 to the minus 10. And when you push the buttons on your calculator, you get a very large number. So that's in seconds. All right, so that is going to be a 2.77 or 2.8 times 10 to the giant number here, 369 looks like. All right, 9 or 10. That is 9, yep. All right, so you would then want to put that in years. So you divide by 3,600 seconds in an hour, and then divide that by 24 hours in a day, and divide that by 365 days in a year. And so you would have that your half-life here is to 2 sig figs, 88 years. All right, so we will not need to do 20.62, but 20.62, you're going to do the same thing. T1 half is 0.693 over K. All right, the K is given, so you simply take your 0.693 divided by the K that's given, which is your 1.03 times 10 to the minus 14, 1 over seconds. So you get a giant number of seconds, which is 6.7 times 10 to the 13. And then you convert that into years, and you get 2.13 times 10 to the 6th years. All right, so you get 2.13 million years for the half-life of Neptunium-237. All right. Let's do number 7. All right, solution of sodium iodide, iodine 131, given to a potato. All right, you got a fraction that would remain undecayed after 5 hours. Okay, what fraction would remain after 5 days? Remember that your NT over NO, this is equal to fraction remaining. So when the question is, what is the fraction remaining? This is what you're looking for. So you have your integrated first order rate law, ln n at time t over n initial is equal to negative kt. All right, so when it asks for the fraction, all we're solving for is that. So we need a time, and we need a k. All right, so what refraction would remain after 5 days? So we have a time, 5 days. If a sample contains 2.5 micrograms, All right, and then it says how many would remain after 5 days. And so they want the fraction and then how much of this mass remains. Well, of course, if it is a fraction of 0.5 or 50% remains, then 1.25 micrograms would remain. All right, so we have to be able to find K. They don't give us K, but they give us the half-life. The half-life is 8.07 days. So T1 half is 0.693 over K. All right, so that's an equation that would be given. All right, and so if you solve for K, K is equal to 0.693 over T1 half. All right, so you just multiply both sides by K, divide both sides by T1 half, and you have that equation. Or you can plug in your number and solve for K. What I'm going to do is take the ln of NT over NO is equal to negative K, which is 0.693, divided by the given half-life of 8.07 days. And we are taking that for 5.0 days. All right, the units have to be the same. The time units have to be the same. So since you have days and you have days, they cancel. If it was years and years, seconds or seconds, it doesn't matter. They have to be the same. They have to cancel. All right, and so you have your answer here. Then you take your e to the x button, and you get your NT over NO. Your fraction that remains is 0.651. All right, so we have not reached a half-life. So we waited 5 hours. It would have been 8.07 hours, days. 5 days, we'd have to take 8.07 days for half of it to be gone. So not half of it is gone. All right, so the amount that remains is more than half. And so it is 0.651. So then you take your 0.651 times your 2.5 micrograms. So you're going to have 65.1% of that left, which is 1.6 micrograms. All right, so there is your fraction remaining, and the amount remaining is 1.6 micrograms that remains. All right, let's try. We'll do 72. 72 is a little tricky. 20.72. All right, so this is where when you go fast, you know what you're doing and you get the wrong answer. All right, so because it says 20% of a sample of zinc decays. All right, so if 20%, this is the tricky part, if 20% decays, that means 80% remains. And your NT over NO is your fraction remaining. All right, so if you're going fast, you're going to mess that up and you're going to put in your fraction as 0.2, but your fraction is 0.8. So as a fraction, that's 0.800 remains. 0.2 decays. All right, so when you have your ln of NT over NO is equal to negative KT, you're putting in the ln of the fraction 0.8. All right, so 80% of the sample of zinc remains in 69.9 days. So now we have a time what is the half-life in days. All right, so again, you know that your T1 half is equal to 0.693 over K. Again, solve for K. K is 0.693 over T1 half. Right? So if you plug that in, if you plug it in for K, you can just solve the equation. So ln 0.800, you can do this number of different ways. If you put in your 0.693 over T1/2, 69.9 days. So when you get your answer, the T1/2 answer will be in whatever units you put in for your time, which in this case is days. Solve for T1/2, and you get 217 days. All right, so that one was tricky just because it gave you the percent that decays, not the percent that remains. All right, 20.74. Sample of silver 112 gives a reading of 875 counts per hour on a radiation counter. After 0.25 hours, the sample has a reading of 400 counts. Per hour. What is the half-life? All right, so again, you have your ln of n at time t, n initial is equal to negative kt. All right, and so here we have the ln of our number of counts after time t is 400. The initial count was 875. That's equal to negative k after a time of 0.25 hours. All right, so this is exactly the same type of question that we had before. All right, so you can then do the substitution. K is 0.693 over T1/2, or you can solve for K and then get your T1/2. It doesn't matter. All right, so your ln of 400 over 875 is equal to negative 0.693 divided by your T1/2. And that is 0.25 hours. So whatever units, again, you have here, that's the units you will get there. So does it ask what is the half-life in hours? Okay, good. So when you push the buttons, you get a half-life. Let's see the answer where I can see it. All right, so we'll push the buttons. So you got 400 divided by 875. We get that fraction. We take the ln of that. All right, so then we take the 1 over x, multiply both sides by T1/2, divide both sides by the ln of 400 over 875. Times a negative 63 times 0.25. And so that is a 0.221 hours. Let's see that. K is 25. Yep. All right, 0.221 hours. All right, so you can check your answer. You can look at 0.25 hours. We had more than half was gone. So we started with 875. We would be down to 437.5. So we're down less than that. So we had passed our half-life. So 0.221 hours, or just 0.22 hours, because it should be 2 sig figs. 74, 76. All right, carbon from Dead Sea Scrolls. All right, so you have a half-life of carbon-14 is 5,730 years. So there's your half-life for carbon-14. All right, so you have an old manuscript. You run a sample of that, and you find that you have 12.1 disintegrations per carbon per gram of carbon. All right, and you know that this is your N at time t. All right, a living material gives a 15.3. So that's your initial. 15.3 disintegrations of carbon-14 per minute per gram of carbon. All right, and so there is your what it is now versus what it started with. All right, and then you already have your half-life, and the question is, how old is it? So you're doing carbon dating. And so to do carbon dating, you have your ln of n at time t versus n initial, and that's equal to negative kt. All right, and so when you're doing carbon dating, you are finding the time. How old is this sample? So you have your 12.1, 15.3, your half-life. So you have your T1/2 is 0.693 over K. All right, when you solve for K, that is K is equal to 0.693 over T1/2. All right, so minus 0.693, the half-life is given, 5,730 years. So when you solve for t, the units are years. So whatever units you have here, that's the units you're going to get for years. So when you push the buttons, you find that it is 1.94 times 10 to the third years old. All right. All right. 2078. Mammoth bones found in Arizona, carbon dating. All right, so they were found to be 1.13 times 10 to the fourth years old. So that is a time. Usually that's what we're solving for. 1.13 times 10 to the fourth years old. What must have been the activity of the carbon-14? All right, so this time we're looking for what was the NT that must have been found from this bone, knowing that our initial carbon reading is 15.3 disintegrations per minute per gram of carbon-14. All right, so you have the same equation, ln, n at time t, and initial is equal to negative kt. All right, except now the unknown is the NT. This is still 15.3, the initial reading of an alive animal. And this is your 0.693 over the half-life. So that is your 5,730 years, which is great because that's how they give us our time. 1.13 times 10 to the fourth years old. All right, so years have to cancel years, or days cancels days, or hours cancels hours. Those units must be the same. All right, so you can push all the buttons on the right. ln n at time t over the 15.3. You get a number. And 1.13 times 10 to the 4th times that. I don't think I have that number. Okay. All right, so then you take your E to the X on both sides. I don't have that number. You just got to multiply it. So you have your NT over 15.3 is equal to 0.255. Multiply both sides by 15.3, and you get your reading. In order for something to be that old, had to be a reading of 3.90 disintegrations per minute per gram. All right, so the units of this number, these units must be the same units. So your NT over your NO, those units must be exactly the same to cancel out. All right, so now we get into a mass energy problems, which I believe are the harder problems in chapter 20. All right, so let's do 20.8. All right, so 20.8 is not a nuclear reaction. That is just a chemical reaction. So in a chemical reaction, we say there is a conservation of mass. Well, there is not a conservation of mass. All right, but let's calculate what that mass is. So we have a sulfur solid plus O2 gas yields SO2 gas. All right, so that is a balanced chemical reaction, not a nuclear reaction. All right, so you have your products minus reactants. You find your delta H for this reaction. It is negative 297 kilojoules per mole. All right, so that is a typical energy exothermic reaction for a chemical reaction. All right, so the question is, what is the change in mass? All right, so we say there's a conservation of mass. There is not. We have Einstein's equation. So E is equal to mc squared. And so the change in energy, which is your delta H, is equal to your change in mass, c squared. All right, and so the units, though, you have to know the units. Your energy is going to be in joules. Your mass has to be in kilograms, and your speed of light has to be in meters per second, because a joule is equal to a kilogram meter squared per second squared. All right, so we put in a negative 297 times 10 to the third joules. We have our delta E in joules. That's equal to our change in mass times 2.998 times 10 to the 8th meters per second squared. So the speed of light is a constant. It will be given. All right, and so when you do that, you get your change in mass is negative. So if you have an exothermic reaction, you have lost mass. If you have an endothermic reaction, you have gained mass. All right, so we have the same sign. So whatever the sign is for your energy, that is the same sign for your mass, because the speed of light is always positive 2.998 times 10 to the 8th meters per second. So you get a negative 3.30 times 10 to the minus 12 kilograms. All right, most of the time we're going to weigh something in the lab. We're going to weigh it in grams. So let's convert that to grams. We have to get rid of kilograms. We need grams. All right, so we're going to multiply that by 1,000. There's 1,000 grams in a kilogram. And so our change in mass is it has lost 3.30 times 10 to the minus 9 grams. All right, our balances weigh to the minus, you get 4 decimals at best. So this is, and the 4th decimal has error. This is 0.12345678330. And so we can weigh, well, not really accurately because this is where the error is at. But anyway, we weigh to the 4th decimal. This is way past that. All right, so we cannot weigh this in our lab. So this is called a conservation of mass, because the mass lost or gained in any chemical reaction is a very small amount. All right, but now we're going to do some calculations with nuclear reactions and see that these are significant masses, much higher energies. Nuclear reactions produce much higher energies. All right, so when we go to 2082 and we have a nuclear reaction where we have an H11 plus H11 yields H21 plus a 0,1e. All right, so that is a positron. A 0,1e is a positron. All right, so we want to get our masses. So all right, now here is where it depends on where you're getting your masses. So this gets to be the difficult part. All right, so if you're using proton, you should be using proton. If you're using proton, you should be using proton. That is great. So those are both protons. All right, you don't have a deuteron mass. So this is a deuteron. You have a proton mass. You do not have a deuteron mass. So to get this mass, you got to take your mass of 2,1 and subtract the 1 electron. All right, so here you have your proton mass, 1.00728. And that's AMU. I prefer to use grams per mole. Same here, 1.00728 grams per mole, right off of table 20.3. Your H21 is off of the table. It is a 2.013451. But here we have to subtract in order to get the deuteron mass and not the mass of the element H21. We want the particle, the nucleus only. We have 1 proton, and in here we also have 1 electron. Here we're doing the proton mass. So the proton is a proton, no electron, just a proton. So here we have to subtract our mass of our electron, 0.000549. All right, and so here is our positron. Our positron has the same mass as an electron, but it has a positive charge. And so this is your 0.000549. And so here we had to subtract the electron from this one. We did not have to do that over here because we are using the proton mass. So when you calculate your delta M, all right, so you have your delta M is equal to your mass of your products. So you add those up, subtract your mass of reactants. You add those up, and you get your change in mass. And your change in mass for this would be a negative 0.00056 grams. All right, so we can actually detect that amount of mass in our lab. We have a number in the 4th decimal. All right, but the question was calculate the change in energy in joules per mole. So delta E is equal to delta M C squared. All right, so before we can put the M in here, we know that this is going to be joules, and so this has to be a kilogram meter squared per second squared. And so you have to convert this to kilograms, so you have to divide by 1,000 grams. All right, and so your energy for this is, so that's minus 4, a negative 5.6 times 10 to the minus 4 minus 3 minus 7 kilograms. So when you do that, your calculator should be 5.6 times 10 to the minus 7. And then 2.998 times 10 to the 8th meters per second quantity squared. And so you have now your energy in joules per mole. So that energy in joules per mole, 5.03 times 10 to the 10th. All right, so then it wants you to calculate, let's see. Give the energy change in MeV per nucleus. So now we have to convert joules to MeV. That is a constant that will be given. 0.6 times 10 to the 13th. Where's that conversion at? Right here. Okay. So you've got your negative 5.03 times 10 to the 10th joules per mole. All right. And so then you have 1 mole is 6.022 times 10 to the 23rd nuclei. All right, so that's how you get rid of moles and you get joules per nuclei. Then you have, there are 1.602, 1.602 times 10 to the minus 13 joules is 1 MeV. And so that's how you get rid of your joules and you get MeV. So that is, you get a negative 0.52 MeV per nuclei. And if you wanted it per nucleon, well, that would be the same because you just have one proton in the proton. All right. So when you do the next one, 20.84, mass defect, you have to know that that is a reaction where your nucleus, in this case nickel 5828, is going to 28 protons plus 30 neutrons. All right. In this case, again, you have your mass here is going to include 28 electrons. You have to subtract 28 electron mass from the mass on the chart. The mass on the chart includes 28 electrons here. All right. You have your 28 protons and your 30 neutrons. And then that will give you your delta M, and then you go delta M times your C squared is equal to your delta E. Remember, you're going to get grams that have to be converted to kilograms before you put it into that equation. And then here, you have to convert it to nucleons. So one nuclei of nickel 58 has 58 nucleons. So your conversion to get rid of your nuclei and go to nucleons, there are 58 things in the nucleus. 28 protons, 30 neutrons. Those are your nucleons. All right. I will post all of the answers to all of the homework.